This one is C8H8O2. It has 5 double bond equivalents. We have an aromatic ring here split into 2 peaks. That is going to be 5H, so it's going to be C6H5. We've got 3H down here, that's going to be a CH3. Pieces left over, C, 2 O's, and a double bond equivalent. So that would be a C double bond O, and an oxygen. That should be all the pieces. Now we can put them down. Now it should be clear to you that there are going to be 2 possible ways that we can arrange this structure. We can have the C double bond O here and the O here, or we can switch them around and have the O here and the C double bond O here. We can tell which way it is by looking at a couple of things. The first thing we can look at is that the observation that a CH2, for example, connected to an oxygen will be at 4.0 ppm, while a CH3, for example, connected to a C double bond O will appear between 2 and 2.5 ppm. The case here is that the CH3 is at 2.0 ppm, or a little bit after. That would indicate that it is indeed next to the C double bond O, which would make this the correct structure. We can get one other clue by looking at the shape of the aromatic region, and you can see it's been split into 2 peaks, centered at around 7.0 ppm. What you can see here is that when an O or other strongly activating group is directly connected to the aromatic ring, that we usually get an aromatic ring that's separated out into 2 separate groups of peaks and is centered around 7.0 ppm. Again, more evidence that we are dealing with a situation where the O is directly connected to the aromatic ring.